Welcome back to session 40. This is going to be the second part of our description of the concept of copulas dependency in the process of modeling multivariate risk. In the first part of this session, we talked about copulas in general. We introduced the notion of two-dimensional copulas. Within those two-dimensional copulas, we focused on the specification of the so known as Archimedian copulas and also the Gaussian copula. Now, recognizing that the first part of this class was pretty heavy in terms of the math that we needed to use and the level of abstraction that it was required, now it's time to have some fun. It's time to take advantage of what we learned, and we're gonna start using a calculator for joint distributions with copulas, and then we will show how those calculators can be used to generating pseudo-random variables for couple distributions. Then we will go to option pricing and value at risk applications of these coupling exercises. So let's get started. Here we're going to present a calculator. We're not going to need to do any math. All the math will be done by Maple. So as always, the first thing we do is that we click that icon in order to restart and load the necessary packages. Now we're going to have two random variables, random variable U and random variable V. This menu will allow us to choose between some very widely used specifications. For instance, we can take a normal distribution and we can have a Cauchy distribution. Now we need to let Maple know that this is the one that we're going to use. Notice that this button is activated and this one is not activated yet. So we cannot move on until we first assign our first random variable and then we assign the second one. And notice that in these windows we see the specification of their corresponding cumulative distribution functions. Now, step 2 is about how to combine these two random variables. So we will go on and pick and choose a copula. Let's say that we start with a frank copula. Once we do that, we need to create the corresponding copula function for the two random variables. And then from there, we get to the joint probability density function. This is fantastic because Maple does all the algebra. We don't have to worry about it. Once we have that, remember that we had two distributions. One distribution had two parameters. It's the normal distribution with a parameter for mean and standard deviation. And the other one is a Cauchy distribution with a parameter reflecting scale and the other one reflecting position. So now we can play with these four parameters. We call them A, B, C, and D in general. So as always, we see how these joint distributions look like as we start playing around with the parameters. Notice that the shape doesn't change, but the scale changes when we change C and we change D. So looking here and in here. Now we can also play with the dependency parameter, and this dependency parameter, as we know, has to do with correlation. So well, this is for this particular coupling. So we can decide to change the way in which we're coupling the functions. Let's say that we take this combo function, then we will get a different PDF, joint PDF, and then notice the distortions that we get, especially in this part of the bell, right? Obviously, this copula is only valid for values of alpha that are in this range. Otherwise, they wouldn't make any sense. So this is interesting in order to realize how parameters are constrained depending on our specification. That's something that we talked about in the previous section, but it was kind of hard to explain back then. Now, just to play around, we can again change distribution. We can go for a log normal. We need to assign both distributions. We could change the way in which we couple them, and we will see what comes out. Here is the PDF, and finally we will end up with something that's expected, that has it will look it from here, it looks normal, but if we look it like here, it really looks like normal. So that's the way in which we're coupling normal and log normal distribution using a Morgenstern coupling. Now, this is very interesting, it's very nice, but not necessarily as useful as we need it. The real application is about being able to generate our random samples. So here's how we get to pseudo-random samples of couple variables. The methodology is described in this box. How we go from our coupling functions and our commutative distribution functions all the way to produce the joint distribution. I'm not spending that much time here, and I'm going to jump directly to how we use it in a specific application. So again, I need to load the package. We will choose a copula. Let's say that we stick with a frank copula. So we get an intermediate function that is required in order to generate these pseudo-random samples. Then we will combine, again, let's say that we take a normal distribution and a Cauchy distribution. So we assign it, and we assign it here. And once this is done, we need to produce the quantile functions that are going to be used for, or as the basis for producing the random numbers. So now, here we have our calculator. We can change the parameters. We're producing the marginal distribution, let's say, the histogram of the marginal distribution X here, and the Y distribution here. We can control for the sample size. This is 600, 400. This is very important in terms of the speed in which you want to work. We can change our correlations as expected, and again, we can play around with the parameters of this distribution. Okay. Make something that looks more like a cloud, like this. Okay, yeah. With nicer dispersion for X. Okay, so we can do the same things that we had talked about before. We can move, let's say, for a log normal distribution. We calculate the quantile functions, and in here we go for the parameters of the distribution. Obviously, since we are in a log normal world for one of the variables, the range is positive for variable y, whereas for variable x, we have it all the way from -infinity to infinity. And this is the way it looks like, as expected. We can, again, control for the size of the distribution. We can control for the dependency parameters. And this is the way this is going to look like. So in the next 10 minutes, we're going to take a break here, just a technical break, but we will go to seeing how we can use these samples for option pricing. So here we can have or define portfolios that are combinations of random variables, and we can define a strike and calculate and simulate our strikes and the premium of the portfolio. Well, so we'll stop here for a second, and we will come back in 2 minutes.